So, good afternoon, all. In previous class, I have discussed about thermodynamic vapor power cycle, right? Like Carnot cycle and Rankine cycle. Now, today we will discuss about, we'll recapitulate about Rankine cycle. So, this is the course objectives. Last class I have told already. The usage of fundamental knowledge on the thermodynamic cycles and fluid mechanics phenomenon present in turbomachinery and combustion for producing electric and mechanical engineering power, right? The operational concepts, principles, features, procedures, and detailed thermodynamic analysis related to components of power cycles, rocket propulsions, as well as steam and power generators. And the third one is a wealthy and real world engineering problems and examples towards gaining the experience for designing and developing power generating systems in engineering practice. So these are already I have discussed in the last class. So now, already I have told about the Rankine cycle, how it works, and what are the major components of Rankine cycles. Now, today again we will recapitulate this method. So, what is Rankine cycle? Rankine cycle is a theoretical cycle on which steam turbine or steam engine works, right? So, it is an ideal cycle for comparing the performance of steam plants, and it is the modified version of Carnot vapor cycle, where the condensation process takes place until it becomes the saturation liquid, right? Now, already I have discussed about this Rankine cycle working principles. Now, today only, now again we have to only recapitulate the what we have done previously. Now, this is boiler, turbine, condenser, pump. Already I discussed. So, the steam produced from the boiler, it is going to the turbine, where it is expanded isentropically or reversibly and adiabatically. And again, after expansion, it will going to the going to the condensers, right? Where the condensation process takes place until it becomes saturated liquid, right? So this saturated liquid again is going back to the boiler by using the feed pump, right? So already we have discussed this: boiler, turbine, condenser, and pump, right? So these are the four processes. 1 to 2 is a turbine, 2 to 3 is a boiler, condenser, 3 to 4 is a feed pump, and 4 to 1 is a boiler. Here, 4 to 1 heat is supplied. Let's say this is Q1, already this is here, and heat rejected Q2 from the condenser. This is Q2. Now, already last class I have told the what are the four processes. This process 1 to 2. See, if you see the process 1.1 here, it may be the condition of steam. It may be dry saturated steam, it may be wet steam, or it may be superheated steam. So depending on the situations, it may vary, right? So 1 to 2 is a reversible adiabatic expansion process. This is the isentropic process where the entropy remains constant. Let's say this is S1 is equal to S2, right? So this is the turbine. Here it will produce turbine work, WT. This 2 to 3 is a condenser where the heat is rejected, and this 2 to 3 is a constant pressure transfer of heat in the condenser where the heat is rejected. Let's say this is Q2 according to the diagram. And this 3 to 4, it is a pump, right? So this is a reversible adiabatic pumping process in the feed pump. And here, this is the pump work, right? WP, that we have already discussed. Now, 4 to 1 is a boiler where the heat is supplied in the boiler. This is Q1. So, last class, I have calculated the efficiency of Rankine cycle. How to calculate the efficiency of Rankine cycle? This is equal to efficiency, already you know, output by input, right? So, what is output here? That is nothing but the turbine work minus pump work. So this will becomes the net work done divided by what is input. We're supplying the heat to the boiler. So this is input, right? So here turbine work, already we have no turbine work. This is 1 to 2 is a turbine. This is H1 minus H2, right? What is the pump work? That equal to H4 minus H3, right? This 3 to 4 is a pump. So this is pump work. Or we can write it here V3 into P4 minus P3. This is a pump work. Heat supply, that is 4 to 1, right? So this is H1 minus H4, and heat rejected is Q2, that is 2 to 3, H2 minus H3. So after calculating all these terms, you have to put it here to calculate the efficiency of Rankine cycle. That already we have discussed in the previous class. So this is how to calculate the efficiency of Rankine cycle, right? We are applying the steady flow energy equations to the boiler, turbine, condensers, and pumps, right? So now already we calculated the efficiency of Rankine cycle. So now using the thermodynamic properties, we have calculated the pump work. So this is the efficiency of Rankine cycle. H1 minus H2 by this is equal to H1 minus H2 by H1 minus H4. This is the heat supply Q1 and this is the turbine work. And here pump work should be neglected because it is a very small quantity in comparison with the turbine work. That's why the pump work should be neglected here. So now the efficiency becomes turbine work by heat supply. So let us solve some numerical based on these Rankine cycles. Now the question is given in a steam power cycle, right? The question is given steam power cycle. The steam supply is at pressure of 15 bar and dry saturated. The initial condition of steam is given P1 pressure 15 bar, right? And it is dry and saturated, right? That means your X1, this dryness fraction should be 1. It is dry and saturated, should be 1, right? The condenser pressure is given 0.4 bar. What is the condenser pressure here? That is equal to P2, 0.4 bar, right? So calculate the Carnot and Rankine efficiencies of the cycle by neglecting the pump work. Here we are neglecting the WP, pump work we are neglecting. So we have to calculate the Carnot efficiency and the Rankine efficiency. So how to calculate? We'll see. Now what we have to do? If you see here we are using the steam tables, right? So from steam table at initial condition pressure 15 bar, this is the saturation temperature. I have told there are 3 tables. One is pressure based table, second is temperature table, and third one is both pressure and temperature is given. This is called superheated table, right? So from steam table, we'll see where is the pressure 15 bar. Now let's say the pressure is given in bar in the steam table. Suppose this is 0.1, 0.2, 10, 15 like that. So if you see where is the pressure 15 bar, the pressure 15 bar, what is the corresponding temperature? That is called saturation temperature. So this is called 198.3 degrees Celsius. So at pressure 15 bar, first you find out the saturation temperature. What is the saturation temperature from the steam table? Now in steam table again, in this column there is a given what is specific enthalpy V is given, specific volume VF and VG value is given. Then HF and HG value is given in the steam tables, and SF and SG entropy value is given. So at pressure 15 bar, what is the value of Hg? That you have to write it here. Why we are calculating Hg here? Because we require H1. So H1 is equal to HF plus AX into Hg minus HF, right? So this is the H1, right? But in the initial condition, first point 1, the dryness fraction, it is dry saturated. This is 1. If you put it 1 here, this HF will be cancelled. So this will become Hg. So H1 is equal to Hg. That's why we are calculating the Hg here, right? Again, at pressure 0.4 bar, that is called condenser pressure, right? So condenser pressure, what is the saturation temperature from steam table? This is 75.9 degrees Celsius. Now, what is HF? If you see in the condenser pressure at 0.2, it is in liquid region, right? So we are considering only HF. There is no Hg because there is a dryness fraction is 0. If you put it dryness fraction 0, H is equal to HF H3. That is called H3. Sorry, that is called H3. H3 is equal to HF plus AX HFG. Here dryness fraction is 0, so that will becomes HF only. So we are calculating HF from the steam table at pressure 0.4 bar, right? Similarly, at 0.4 bar, what is SF? This is the value of SF, specific entropy, and this is the value of SFG, right? So at pressure 15 bar, what is the saturation temperature? 198.3 degrees Celsius. So this is become T1, temperature T1, convert to Kelvin. All the temperatures in degrees Celsius, when you are calculating the efficiency, will convert to Kelvins, right? At temperature T2, already we calculated from saturation temperature from the pressure 0.4 bar. Now what is the efficiency of Carnot cycle? T1 minus T2 by T1, highest temperature minus lowest temperature by highest temperatures. So we put it here, you will get the value that is called 25.9%. So this is the efficiency of Carnot cycle. Now we will find out the efficiency of Rankine cycle, right? Now to find out the efficiency of Rankine cycle, we should know the temperature entropy diagram of a Rankine cycle. This is very important, right? First, we have to draw the temperature entropy diagram for Rankine cycle. Already we have discussed for the temperature entropy diagram. If you see, the initial condition of steam is given dry and saturated, right? I have told in Rankine cycle there are three conditions. One is wet steam, second is dry saturated steam, and third one is superheated steam, right? So if you see, the steam is given dry and saturated, so the point should be here. The point one should be here. This is dry saturated. So this is the turbine. This one is the condenser. This is 1, 2, 3. This one is the pump, 4, and this is the boiler, 1. Right? Here, entropy remains constant. Adiabatic process, reversible and adiabatic process. S1 is equal to S2. Here S3 is equal to S4. Right? Here heat is supplied. That is, let's say Q1. Heat rejected is Q2. Right? So this is the turbine work, and this is the pump work. And here the question is given. If you see, we are neglecting the pump work, right? Now we will neglect the pump work. WP is equal to 0. So what is the efficiency of Rankine cycle? The efficiency of Rankine cycle is equal to net work. The efficiency of Rankine cycle is equal to net work by heat supply. That is equal to turbine work minus pump work divided by heat supply, right? That equal to pump work should be 0. So this is turbine work by heat supply. So what is the turbine work? That equal to H1 minus H2, right? So what is the pump work? Here the pump, sorry, what is the heat supply here? Heat supply is H1 minus H4. So this is the heat supply, right? Now we'll see what is the value of H1, H2 and H4. If you calculate H1, H2, H3 and H4, your problem will be solved. So what I have to do here? So this is the efficiency of Rankine cycle. This is H1 minus H2 by H1 minus H4. This is the efficiency of Rankine cycle, right? Now we have to calculate the value of what is H1, what is H2, what is H3 and what is H4. Now already we have calculated what is the value of H1. You see here. So what is the initial condition? At pressure 15 bar and dryness fraction X is equal to 1, what is Hg? So this will becomes H1. So this is the value of H1, 2789.91. So this is the value of H1, 2789.91. Because H1 is equal to Hf plus X into Hg minus Hf, right? Here dryness fraction is 1 because the question is given dry and saturated, right? So this will becomes Hf will be cancelled. So this will becomes Hg. So H1 is equal to Hg at the pressure of 15 bar. From the steam table, at the pressure 15 bar, what is the value of Hg? That equal to H1. The value is 2789.8. 2789.9 kilojoule per kg. This is the value of H1. Right? Now, the question is how to calculate H2. Because the 2.2 will be in wet steam in the liquid and vapor region, right? If you see the diagram, the 2 point will be in liquid and vapor region. So H2 should be calculated from HF2 plus X2 into HFG2, right? So at 2 means the boiler pressure is given 15 bar and the condenser pressure, 2 means condenser. Condenser pressure is given 0.4 bar. So at 0.4 bar, what is the value of HF from steam table that you have to put? And what is the value of HFG2 that you have to put at the pressure 4 bar, 0.4 bar. But how to calculate the value of dryness fraction at 0.2 that you have to calculate? So how to calculate the dryness fraction? And we know, if you see the TH diagram, already I have drawn here that this TH diagram. If you see, this is the TH diagram. You see here, this is 1 and this is 2, right? So here the entropy remains constant. S1 is equal to S2. This is a reversible adiabatic expansion process which will produce turbine work here, right? And here the entropy remains constant. This is isentropic process, right? So isentropic process means S1 is equal to S2, right? So S1 is equal to S2. What is the value of S1 here? Here same procedure, S1 is equal to SF plus X into SG minus SF. So here X is equal to 1. If you put X is equal to 1, this SF will be cancelled and this S1 is equal to SG. So at pressure, this is 15 bar and this is 0.4 bar. So at pressure 15 bar from steam table, what is the value of SG? That equal to S1. This is the value, right? That is equal to S1. And that equal to what is S2? SF2 plus X2 into SFG2. And this SF2 and SFG2 at the pressure 0.4 bar. From steam table at pressure 0.4 bar, what is the value of SF and what is the value of SFG? We put it here. After putting the value here, all the values, from this you calculate what is the dryness fraction at 0.2. That is called X2. And that should be coming in 0.815. It should be less than 1. So after calculating the dryness fraction at 0.2, calculate what is H2. So H2 is equal to HF. This is HF. At what point, at what pressure this is? This is at pressure 0.4 bar. What is the value of HF? Plus X into HFG2. This is at the pressure of 0.4 bar. 0.4 bar. So this is the value of H2. Right? So after calculating the value of H2, we should calculate what is the efficiency of Rankine cycle here. Already H1 minus H2, H1 minus HF2. And this is the efficiency of Rankine cycle. You put the value of in the all the values of H1, H2 and H4. You put it here and you get the answer. This is the value of Rankine cycle. This is how to solve the Rankine cycle problems. Let us solve one more problems. See, the question is, in a steam turbine, steam at a pressure of 20 bar and temperature 360 degrees Celsius is expanded to a pressure of 0.08 bar. Right? The initial condition of steam, pressure P1, is given 20 bar and temperature T1 is given 360 degrees Celsius. Right? Is expanded to a pressure of P2 that equal to 0.08 bar. 0.08 bar. It then enters in a condenser, right? Where it is condensed to a saturated liquid water, right? So the pump feed work the water into the boiler. Now assume all the processes to be ideal. That means we are assuming the ideal processes, and we have to find out what is the net work done per kg of steam. So what is the net work that equal to per kg of steam, per mass of steam, that you have to calculate. What is the net work done per kg of steam and the cycle efficiency. What is the efficiency of Rankine cycle that you have to calculate. Now if you see the TS diagram, so this is the saturated liquid line, this one saturation liquid line, and this one is saturation vapor line. Saturation vapor line, right? Now the initial condition of steam is given pressure 20 bar and the temperature is given 360 degrees Celsius, right? So the condition of steam is here is superheated steam, because it is not a wet steam, it is not a dry steam. Here it is given pressure and temperature, so it will become superheated steam. Now the point 1 should be here at this point. At this point the pressure is 20 bar and temperature 360 degrees Celsius. So this is the condition of steam, superheated steam. Now after it is expanded isentropically in a turbine, it is going to the condenser pressure. This is point 2. Yes. So after expansion, it will becomes the wet steam. This is point 2. Point 2 should be here, right? Then it is going to the condenser, going to the pump. Again, it is fed to the boiler, right? So here the condenser pressure is given 0.08 bar and the boiler pressure is given 20 bar. We have to calculate the net work done per kg of steam and what is the Rankine cycle efficiency. Now what we need, if you see here the boiler pressure is given P1 is equal to 20 bar, condenser pressure P2 0.08 bar, right? So now from steam tables you see at pressure 20 bar and temperature 360 degrees Celsius. What is the value of H? If you see in a steam table, there is a pressure table, one more is temperature table, and third one is both pressure and temperature should be given. And here in pressure table, here it is given HF, HG, SF, SG, like that the value is given. Temperature also same value is given. But in pressure temperature, only H value is given, S, U, internal energy, and a specific volume is given, right? So from steam table, you see at pressure 20 bar and temperature 360, what is the value of H? That will becomes H1. That is the value of H1. Again, at same pressure 21 and temperature 360 degrees Celsius, what is the value of entropy? S. That is becomes S1. Right. Now, if you see at pressure 0.08 bar, this is a condenser pressure, 2 to 3. It's a condenser. So, what is the value of H3 at that point? If you see this diagram, these 3 points will be here, right? Where the dryness fraction is equal to 0. Now, what is H3 here? HF plus X into HFG. Correct? Now, if you are putting the dryness fraction is 0, that will becomes HF. So, H3 becomes HF. At what pressure? 0.08 bar. So, from steam table at pressure 0.08 bar, what is the value of HF? That will becomes H3. Right? Now, what is the value of SF? That will becomes S3 in a similar way. Right. Now, at same pressure at 0.08 bar, what is the value of HFG that you have to calculate? Not calculate, taken from steam tables. What is the value of SG? What is the value of VF, specific volume VF, and what is SFG? So, these all values are taken from steam table at pressure 0.08 bar. So, already H1 is known and H3 will be known. Now, remaining is H2 and H4 that you have to calculate. What is the value of H2 and what is the value of H4? So, our aim is to calculate all the enthalpies at each point. What is H1, H2, H3 and H4? So, H1, H3 value should be known. Now, we have to calculate H2 and H4. So, how to calculate? If you see here, there is a specific entropy, right? The entropy remains constant. S1 is equal to S2 and here S3 is equal to S4. Right? So, now, for this H2, that equal to HF plus X2 into HFG2 is equal to, right? Now, at pressure 0.08 bar from steam table, you find out the value of HF and HFG2. But what is the value of dryness fraction here? That you have to calculate the H2, right? Now, what you have to do here, isentropic process 1 to 2 is isentropic process, right? S1 is equal to S2. Now, put it here, S1 is equal to S2, right? Now, what is the value of S1? This is at a pressure of 20 bar and temperature 360 degrees Celsius. Find out the value of S. That will becomes S1 from steam table. This is the value of S1, right? And that equal to S2. S2 is SF plus X into SFG2, right? And this is at a pressure of 0.08 bar. 0.08 bar. What is the value of SF and what is the value of SFG? And put it here in this equation and calculate what is X2. X2 becomes 0.838. Now, how to calculate H2? H2 is equal to HF plus X into HFG2. Now, this HF and HFG at pressure 0.08 bar. Now, from steam table at pressure 0.08 bar, what is the value of HF? We put it here, and the value of HFG, put it here. And dryness fraction already we have calculated, right? 0.838, put it here. So, this will becomes the value of H2. Now, we have calculated H2, H1 and H3, right? Only unknown is H4. How to calculate H4? Now, this should be calculated from pump work. Pump work, you should know WP is equal to H4 minus H3, or we should write it here V3 into P4 minus P3. That is written here H4 minus H3. Nothing but 2. It is same as H2. Right? That equal to, because the pressure is, this is a condenser, because, why 2? Because 2 to 3 is a condenser. So, this is same constant pressure. That will become 0.08 bar, it is given constant pressure. So P2 is equal to P3. Okay. So V into P1 minus P2, right? Because your P4 is equal to P1 and P2 is equal to P3. So instead of P4, you should write here P1, this is P2, which we written here. P1 is equal to P2. So from steam table, you see what is the value of VF at pressure. At what pressure? 0.08 bar. What is the value of VF? We put it here, right? Into what is pressure P1? 20 bar. Pressure P2 0.08 bar. Now calculate what is the pump work from these equations. This will becomes 2.008 kilojoule per kg. Now this pump work is equal to H4 minus H3. H4 minus H3. Now this pump work already calculated. H3 already known. Now calculate H4. So H4 is equal to pump work plus H3. So this equation will give the value of H4. Now see, this H4 is equal to pump work plus the value of H3. What we have calculated in previous slides. So this will becomes the value of H4. Now what is the turbine work? H1 minus H2. Put it here. Calculate the turbine work. What is the net work done? The turbine work minus pump work. So this will becomes the net work done per kg of steam. Whatever the question asked, first point, calculate the net work done per kg of steam, kilojoule per kg. We have to calculate the efficiency of Rankine cycle. Right. So what is the efficiency of Rankine cycle? Net work done by heat supply. Net work done already we calculated 961.61. Now what is the heat supply here? This will becomes H1 minus H4. So H1 already known and this H4 already known. Put it here. It will becomes 2983.41. So the efficiency of Rankine cycle will becomes 32.5%. So this is the numericals based on the Rankine cycles. This is one type of numerical. This is the condition of steam is superheated. Previous what we have done, the condition of steam is dry saturated. Now here we have done the condition of steam is superheated. Now let us solve one more numerical. What is the question? A simple Rankine cycle working between two pressures. One is boiler pressure and second is condenser pressure. So boiler pressure is given 28 bar. This is the boiler pressure 28 bar and condenser pressure is given 0.06 bar. The initial condition of steam, this is the initial condition of steam, is dry and saturated. That's why the point 1 should be here, where the dryness fraction is equal to 1. The initial condition of steam is dry and saturated, right? Now, what do you have to calculate? Calculate the cycle efficiency, right? What is the Rankine cycle efficiency? What is the work ratio? What is the work ratio? And what is the specific steam consumption that you have to calculate? You have to calculate the Rankine cycle efficiency, work ratio, and specific steam consumption. Now, how to calculate? The initial condition of steam is given here, pressure 28 bar and dryness fraction 1. And the final condition of steam is given pressure 0.06 bar, right? But here we don't know the dryness fraction, right? What is the value of x2? That you have to calculate first. So this is very simple. What we done in previous class, previous slides. So from steam table at pressure 28 bar, right? So calculate the value of H1 because H1 is equal to HF plus X into HFG. So this will becomes Hg minus HF, right? If you put the X is equal to 1, here HF will be cancelled. Now what is the value of Hg? At pressure 28 bar, what is the value of Hg? That will becomes H1. Similarly, you have to find out the value of S1 from steam table. This is H1 and S1. Now, at condenser pressure 0.06 bar, what is the value of this H2, HF? Because at 2 and 3 point HF will be same, right? This is the value of HF from steam table at 0.06 bar, and this is the value of HFG from steam table, and this is SF and SFG, right? And this one is the VF. at 0.06 bar. Now all you know, this 1 to 2 is a isentropic expansion process, right? S1 is equal to S2. What have we done in the previous previous problems? So same way, S1 is equal to S2, right? S1 already taken from steam tables at pressure 28 bar. This is the value of S1, and S2 is equal to SF plus X into SFG2, right? So this SF at pressure 0.06 bar, 0.06 bar. This is the value of SF, and this is the value of SFG2. Put it here and calculate the value of X2, dryness fraction. So after calculating the dryness fraction, what is the value of H2? How to calculate? Already we know H2 is equal to HF plus X into HFG2. Right? Now substitute the value of X2 here and calculate the value of H2. So this will becomes 1910.27 kilojoule per kg. What is the turbine work? Then H1 is equal to H1 minus H2. So put the value of H1 and H2, we will get the turbine work here. So after calculating turbine work, what is the heat supply? Heat supply is actually heat supply. Why we require? Because the efficiency will be equal to net work done by heat supply. So heat supply is H1 minus H4. But we don't know the H4 value. We have to calculate the H4, right? So what is H4? Already we have discussed. The pump work is equal to H4 minus H3, and that equal to VF into P1 minus P2. We have discussed in the previous numericals, previous problems. So from this you calculate what is the pump work. What is the value of VF at 0.06 bar at pressure? What is the value of VF? Put it here. And what is the pressure? P1 28, pressure P2 0.06. Then we will calculate the value of pump work. And this pump work is equal to HF. Sorry, this pump work is equal to H4 minus H3. Right? So what is the value of H4 here? The pump work 2.79 plus H3. Nothing but HF at pressure 0.06 bar. So this is the value of H4. So the net work done is equal to turbine work minus pump work. So turbine work already we have calculated. This is the pump work. So this is the value of net work. So the efficiency will be net work done by heat supply. From this we can calculate the efficiency of Rankine cycle. That becomes 33.57%. Next question is to calculate the work ratio. How to calculate the work ratio? The work ratio is nothing but the ratio of net work done by turbine work. The work ratio WR that equal to net work done divided by the turbine work. Right? So net work done already we have calculated. This one net work done, and this is the turbine work. You should find out the value of work ratio. Since this is a ratio, so there is no units for this. Next, specific heat steam consumptions. So what is the specific heat steam consumption? This is nothing but the reciprocal of net work. This is the reciprocal of net work done. So 1 by net work. So it will becomes 1 by net work is already we have discussed the net work done 888.94. Right, and it will becomes kg per kilowatt hour. That's why we are multiplying 3600 to convert to second. So this will becomes the specific steam consumption. So this is how to solve the problems based on the Rankine cycle. So this is the Rankine cycle problems. Similarly, there are other problems also available. This is one more problem, one more type of problem. What is the question? The question is a Rankine cycle operates between two pressures 80 bar and 0.1 bar. The maximum cycle temperature is given 600 degrees Celsius, right? And the steam turbine and condensate pump efficiencies are given. Here somehow little difference from previous questions. Here the turbine efficiency and pump efficiency will be given. The turbine efficiency is 0.9 and the pump efficiency is equal to 0.8. The efficiency of turbine and pump is given, right? Calculate the specific work and thermal efficiency. And here you see here the relevant steam table is given. What I have told in the previous section, this is a steam table. Here table is given, right? At pressure 0.1 bar and 80 bar. Then if you see here at pressure 0.1 bar, this is the saturation temperature. At pressure 80 bar, this is the saturation temperature. And these are the values of specific volumes BF and BG. This is the HF and HG, specific enthalpy, and HFG, enthalpy of vaporization. and this is specific entropy value SF, SFG, and SG. And this table will be the superrated table, because if you look at this, the condition of steam is given here. The initial pressure is given 80 bar, and the maximum temperature is given 600 degrees Celsius. And initial condition at point 1 is just a superheated steam, and the superheated table is given here directly. What is the value of V, specific volume? What is the value of H, superheated enthalpy? And what is the value of entropy? These all values are given. If it is not given, we can use the steam tables. Now we have to calculate the condition of initial. Here the condition of steam is given 80 bar. Here the temperature is 600 degrees Celsius. 600 degrees Celsius, right? Now, if you look at this, what is the value of H1 here? At pressure 80 bar and temperature 600 degrees Celsius. Now, what is the value of H1? If you see the table, this is a superheated table. Now, here at pressure 80 bar and temperature 600, what is the value of H? 3642 kilojoule per kg. So, this will become H1. What is the value of S? 7.02. This is the value of S2. S1. Now, if you see here, this is S1 is equal to S2. If you put S1 is equal to S2, this will becomes already calculated from steam tables, right? SF plus X into SFG2. Now, at what pressure this is? At pressure 0.1 bar. At pressure 0.1 bar, what is the value of SF? If you see here, at pressure 0.1 bar, what is the value of SF? 0.6488. See, 0.6488. Now, at pressure, same pressure 0.1 bar, what is the value of SFG? Now, SFG is this 7.5006. If you look at this is 7.5006. What we have done in the previous problems. Then you calculate what is the value of X2, dryness fraction. This will becomes at the point 2. Here, dryness fraction will becomes 0.85. Right? Then you calculate what is H2. That equal to HF plus X into HFG2. Now here X already calculated 0.85. 0.85. Already we have calculated the X. 0.85, right? Now at pressure 0.1 bar, what is the value of HF? 191.9. What is the value of HFG2? HFG 2392. So here 191.9 at pressure 0.1 bar, and this is the value of HFG. Now substitute here, calculate what is the value of H2. Now this is the value of H1 and H2. So after calculating the value of H1 and H2, what is the turbine work? That equal to H1 minus H2. So calculate the turbine work. But the turbine efficiency is given 0.9. So what is the actual turbine work? So 0.9 into H1 minus H2. This is the actual turbine work. So this is the difference. Now this is the difference between this efficiency, turbine efficiency, and previous what we done in the previous numericals. So if the efficiency of turbine and pump is given, find out the actual turbine work and actual pump work. So multiply 0.9. This will becomes 1275 kilojoule per kg. This is the actual turbine work. Now what is the pump work? Pump work already we know is equal to VF, that is V3 P4 minus P3, or we can write V3 P1 minus P2, right? So this V3 at 0.1 bar, what is the value of VF? And this is P1 is given 80 and P2 is given 0.1. Now substitute here, calculate the value of pump work. Now this pump work, this is a ideal pump work, not actual pump work. Now what is the actual pump work? Actual pump work is equal to ideal pump work by pump efficiency. Already we given in the question pump efficiency 0.8, and divide this. This is actual pump work. Okay. Now we are going to use the value of actual turbine work and actual pump work, not ideal. Right. Now what is the specific work? That's nothing but the net work done. So net work done is equal to actual turbine work, that is 1275, minus actual pump work 10.09. So this is the specific work or net work done. It becomes 1264.91 kilojoule per kg. So this is the first answer. So what is the thermal efficiency? Net work done by heat supply, right? So net work done already we have calculated. What is the heat supply? H1 minus H4. So what is H4? That equal to pump work. This will pump work plus H3. So H3 already known. pump work already known. Actual pump work 10.19, 10.09. I calculate what is H4. This is pump work plus HF3. So this is the value of H4, 202. So after finding the value of H4, substitute here. So this is the value of efficiency of Rankine cycle. This is the value of H4. This is turbine work, net work, and this is H1. So after putting all the values, turbine net work done, H1 and H4. So this is the value of Rankine cycle, 36.8%. Right. So this is all about the numericals based on Rankine cycles. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.